first of all, I'd like to thank the organizers for giving me the chance to present the talk that I was meant to give last year in QPL in Japan. Actually, maybe this is an excuse for the over-the-top anachronistic decorations that are sparsed around, having missed the chance. Hopefully it'll bring back some good memories for some of you and keep the others awake until the coffee break. Actually, considering the inflation in the sort of rejection rates for QPL, I think it would be a good strategy to get yourself invited in 5 years' time. But then maybe it's not worth the cost. So I don't know. Anyway, depends what the cost is, I suppose. Classification is quite a powerful means of sort of learning things in maths and physics. A really good example of this is Mendeleev's periodic table, where the elements are sort of sorted by atomic number and sort of valency and electronic properties. And it sort of gives a lot of insight about matter because we have a very clear picture where we can see all the different elements and how they fit together. And in fact, in the foundations of physics, foundations of quantum theory, we have a bit of a rich situation where there are a lot of these theories that are a little bit quantum-like in nature. So for example, stabilizer theory that I guess most of you are familiar with, the qudit version that Dan was talking about, I'll talk more about later. Spec and toy theory, actually they have there's generalization of this for qudits, which I call the Spec and theory for dits, which I'll present a bit later. Other things like Van Enk's toy theory, modal quantum theory, box world. And it would be nice to have a sort of formalism to sort of describe these in an operational way, these different theories. So what I mean by an operational theory is the standard idea that you have sort of states, which are like preparations of physical objects, processes which are transformations of these physical objects, and sort of an observable measurement effect kind of aspect as well. And fortunately, we do have sort of a formalism for this, which is very general and quite appropriate, which is the categorical quantum mechanics. So just a disclaimer, I also go downwards for my diagrams for some reason. I don't know where I picked this up, but so I'm making guys there. Oh yeah, so the sort of, you can use the symmetric monoidal categories, sort of dagger compact forms or whatnot. And actually, the formalism is already here, and the observable structures, which is what I call the dagger special commutative Frobenius algebras, and all this mathematics, which I'll brush over, I guess, in this talk, is here. And you can use this to describe these operational theories in quite a general and powerful way. So within this formalism, I'm sure a lot of you, some of you at least, will be familiar with what we call phase groups, which are the key element that I use in my classification, as we'll see later. And a phase group, what it is, so first of all, you can define classical states, which are just the sort of states that are copied by these sort of copying maps, which are sort of like the analog of classical sort of basis states. And then the unbiased states, which obey this equation. And if you restrict these sort of phase maps, which are sort of states put into the copying, so put into the sort of observable structure copying, to the unbiased states, you get an abelian group called the phase group. And this is sort of a very useful classification tool, which tells us a little bit about the composition of processes in a physical way. And as some of the talks, like Wolf's talk, for example, have mentioned, it has things to do also with non-locality and sort of invariable model emissions, and maybe we'll come back to this. So I'm sort of presenting this framework, which is based heavily on Bill Edwards' work, sort of generalizing it to higher dimensions, I guess. And I'm introducing this sort of what I call mutually unbiased qudit theories, which is just the generalization to qudits of Bill Edwards' work. And this sort of, these comprise of a dagger symmetric monoidal category, and then a sort of qudit-like objects tensored together with the unit, or sort of the objects of this category. And then the observable structures are all mutually unbiased and have the same number of classical states and the same phase group. So it's sort of a restriction, but already these provide a number of interesting examples of physical theories. And the states are all the classical states of some observable structure. So there's this ZX calculus that I'm sure a lot of you are familiar with, and we've talked about a lot. It's been mentioned a number of times in this conference. And in fact, it's sort of restricted to qubits in its current form. It's the way Ross and Bob sort of first presented it. But there's no reason not to extend it to qudits. And in fact, this is provides quite a useful tool to analyze these types of theories. So like this is now the qudit ZX calculus here. And so the main difference basically is just that you have, instead of having just one phase, you have a number of different phases. And they sort of the colors commute in slightly different ways. And so sort of, you can have a bit more of a, so if you excuse the block sphere cherry tree illustrations, you can have a bit of a feel with these things if you look at them in sort of Hilbert space. So these are sort of the mappings of these diagrams into sort of matrices. And I'll give you a bit of an illustration for qudits because this might seem a bit complicated at first. So if you have sort of, this is a red dot, I guess I can use red and green. I normally do this for green, right? But here I suppose I can use the colors. So if we have a red dot with phases, say alpha 1, beta 1, this gets mapped by the ZX calculus. Hopefully this will provide some sort of intuition for those of you who are not familiar with these things. To 1, e to the I, alpha 1, e to the I, beta 1, sort of zeros in the other ones. So that's sort of the red map. So that's a state in the system, since as you remember I'm going downwards. And sort of if you take, so I'm just going to give another example, a sort of green map, say, well, I should say alpha 2, beta 2. Yeah. This in calculus gets mapped to a sort of matrix.
Sorry, if it's a state, shouldn't it be a column vector? Looks sort of like
oh, yes, sorry. I had them the other way around, right? I'm glad someone caught me on that because that would have been the whole talk no listens. Okay. Yeah, so this is the one that's e to the I alpha 2, e to the I beta 2. So this is the matrix, this is the transformation. And you can define the C naught, for example, as I defined it here, so where you get sort of the identity and then permutations of the identity. So what I mean by P1 of identity is something like this, for example, in 3 dimensions. And so this generalizes sort of Ross and Bob's calculus, and you can have it for any dimension. And this sort of, for now we'll study mostly qudits, I guess, but you can define this for any dimension, and it's sort of interesting to study these toy theories using this. So the next thing is that it's a sound calculus for quantum mechanics, and it's also universal, and that's a fair bit harder to prove than in the qubit case, because you have to use sort of results from the literature in sort of universality of quantum gates and show that these families of gates are contained in the calculus as well as the C0 gate. And it's not a trivial proof, but it follows through. But I have no completeness results like sort of Miriam's result for stabilizers being, so ZX calculus being complete for stabilizers. There's no equivalent, so I'm sort of leaving it and hoping Miriam will eventually get on the case. Okay, so now I'll introduce what luckily Dan has introduced before, because I'll be very brief, qudit stabilizer theory. So these are just basically the eigenstates. So I'm just going to talk about the qudit case now. I'm only going to be restricted to dimension 3 for the rest of the talk, just because we have not enough time. But the article talks about other dimensions a little bit. So basically the states are these sort of eigenstates of the qudit xz, xz, and xz squared operator, which are, I'm not really going to talk about this very much. And the sort of Clifford group generators, the Clifford group is what maps the sort of stabilizer states to sort of the Pauli group to itself. And it's generated by these sort of maps. And the Pauli measurements of the operators is sort of the measurement side of the theory. And in fact, you can illustrate this completely as a sort of using this ZX calculus, but just restricting the phases to the relevant phase group. Now what's the relevant phase group? In qudits it's Z3 cross Z3, and this sort of gives you a depiction of the stabilizer theory as sort of using these sort of two toruses And the states, these are just the states, the 12 sort of pure states, which are the stabilizer states, and they get transformed to each other using the transformations. In fact, this generalizes to higher dimensions as well. You can picture this.
What does the torus represent?
So the torus is the torus is the phase, is the quantum theory, sort of the body. So because quantum theory in this phase group representation is a d-torus. So the phase group for quantum theory is d-torus. So these the sort of the phase group for qudit quantum theory is these two toruses. There's sort of two torus. Is a torus, sorry, and then if you use two of them for the x and z observable, then you have these two torus that are right. So this basically, this is the phase group for the z observable, and this is the phase group for the x observable for quantum theory, the torus. And then if you restrict to these points, you get the phase group, you get sort of the eigenstates of the qudits. Okay, so moving on very quickly to the Spec and Streetwork theory for trits. So I'm assuming most of you are familiar with sort of standard Spec and toy theory. And in fact, it generalizes to higher dimensions, but you have to get rid of the sort of knowledge balance principle and replace it with a sort of principle of classical complementarity, which sort of defines Poisson brackets between certain quantities, and if the Poisson, you can only jointly measure the Poisson brackets of quantities that come together. But you can actually look, and so the transformations are permutation matrices acting on the epistemic states. So it's a hidden variable model in the same sense as Spec and toy theory, except now you sort of have these maybe 9 sort of boxes that your ball can be in if you want to think about this. And the ontic state is sort of one of these possibilities. An epistemic state, since we have ignorance about the system, you know, for example, if you're in this epistemic state, that the ball will be in this sort of row here. And there's sort of 12 of these epistemic states, and the value transformations are permutation matrices acting on these states. And measurements correspond to row of this matrix, in a sense. So So measurement is a little bit delicate to describe in detail, but that sort of gives you an idea. So once you have these epistemic states written, in fact, you can, so before, with stabilizer theory, you can sort of extend the work that Bill did and define what I'm calling D-stab, which is sort of d-dimensional stabilizer, which is this sort of symmetric monoidal category with observable structures, et cetera, where you restrict the phases for stabilizer theory. And you can also introduce D-spec, and this is sort of a subcategory, sorry for my writing, a subcategory of finite relations, the category of finite relations, where sort of objects are the sort of single element object, and these sort of d-squared tuples, and the morphisms include sort of permutations of this, together with the copying and together with the copying map and the sort of deleting map. So if you read the paper, things will be more clear. Okay. And so here you can describe Spec and toy theory and stabilizer theory using the ZX calculus. And these are the sort of copying maps that I was talking about. And in fact, they map exactly. And so we can get back a known result that people have achieved, David Gross and others have sort of come to with Wigner functions that Dan mentioned briefly as well. And you can, using only these categorical definitions, show the equivalence of, the operational equivalence of Spec and toy theory for qudits and stabilizer theory for qudits. Well, for trits, I guess, and qudits. And this is sort of how you go about it. So what are we left with? So we've started constructing this very incomplete for now periodic table of mutually unbiased qudit theories. And so the case for sort of 2 dimensions was already known. And there's only just 2 possible phase groups, Z4, which gives you qubit stabilizer theory, and Z2 cross Z2, which gives Spec and toy theory. And there's no others. But as soon as you go in higher dimensions, the situation is more confused. So for example, we don't really know what Z9 would look like. We know that Z3 because Z3 is both qudit stabilizer theory and Spec and story theory in dimension 3. And there's some results for sort of higher dimension qudit theories. But all these theories that I mentioned before, it's not known whether we can fit them. Boxwell probably we can't fit in here. But some of them might, and I'm working on this currently. And also it would be nice to have, so there's sort of two ways we can go about this. One is to look at sort of these different theories and look at what they look like. And there's a whole variety of these quantum-like theories. Study their features, try to understand sort of what the phase group means to do with contextuality and other features. And the other aspect, which is what I'm currently doing, is looking at a number of already existing quantum-like theories and trying to fit them into this table. And hopefully it'll fill up and it'll provide some insight, sort of like the standard periodic table. Okay, thanks. Let's read it. Yeah.
Yes. So you speak about the generalized phase group if you go back. So that one at the bottom would be the phase group for qudit stabilizer theory.
So it's a subgroup, an abelian subgroup of this.
Do you know what that subgroup looks like?
I do for dimension 4. I have it explicitly. For dimension 5, I know what it looks. You sort of do. It sort of generalizes this picture quite well, except instead of having just two toruses, you have d-toruses, so they're harder to picture in your mind, right? Because d-toruses are sort of not three-dimensional things. And sort of it's subgroups of these d-toruses, which have a certain pattern. So I have ideas anyway. But it doesn't seem like they're anything particularly elegant, which seems surprising.
But you don't really need them to be elegant,
No,
as long
no.
as they're like non-trivial algebraic extensions. You can.
Yeah, sure.
It's
You can
secret.
Yeah.
That's what you want to know.
Yeah, sure.
Because that's the point where it would be really interesting to have a proper characterization.
That's right. Yeah.
Did you want to ask a question?
Any question?
So in your axioms, I didn't notice you showed them quite
Yeah.
clearly, right?
Just solve it.
So in the qudit ZX calculus, it's quite important to have this order decomposition
Yeah.
of H. Do you have anything equivalent?
So I have. So no, but I mean, but that's sort of for completeness, right? And I guess I'm not claiming,
Yeah.
but yeah.
Well, of course, you can prove many more interesting
Sure.
theorems, right?
Sure. Yeah, that's something that I should add. But I also have another axiom where I define an S-gate, which is a bit like the stabilizer S-gate. And this is one axiomatic system. Let's put that. There are others. This is the simplest one. Yeah.
So you had a big red cross on your sort of periodic table of theories.
Yeah.
Do you know which groups are allowed and which are disallowed? Is that cross a group that you know?
No, that clause is just saying that this is the full situation for two-dimensional.
Oh, I see.
And that's understood.
Because you've run out of groups.
Yeah, run out of groups. But
So
it's just to contrast the two-dimensional case, which is sort of fully understood, with higher dimensional case, which is
So you should in principle be able to construct this for any cyclic group, is that?
abelian, yeah.
Any
Abelian.
Any abelian group.
Any ideas how from a phase group you build a theory? Because if such a recipe would exist, you would be done.
Yeah, that's right. Yeah, so I'd have to try this with Z9. I've not looked much. As I said, I've been more doing it the other way, sort of trying to fit in theories. But I have some idea. We should chat anyway.
Well, I mean, have you thought about the non-abelian group? Because there are some things you can say about it.
Thought about it, but not anymore.
Okay.
But again, we'll chat. Cool. Okay.
All right, if that's all the questions we have. Okay, and so we have coffee now, and we restart